Hi, everybody, and welcome to Lesson 4.3. Today, we're going to be investigating nonlinear functions. So far, everything we have done has been linear functions. We've looked at linear functions on a graph, we've looked at linear functions in a table, and we've also written equations for linear functions. But what about nonlinear? So today we're going to explore some patterns with the graphs, the equations, and the tables of nonlinear functions. Let's get started. First, let's look at the graph. What's the difference between a graph that's linear and a graph that's nonlinear? Well, just like the first four letters in the word linear spell line, anytime I see a graph of a straight line, it's linear. So as long as that line goes forever straight in both directions, whether it's, pointing up, pointing down, vertical, horizontal, any direction, it's linear if it's a line. Well, just like the prefix non means not, nonlinear means not straight line. So taking a look at some of these examples, here we have lines that are not straight. They're curved, or we have a V shape, but they're not straight in both directions. So if you're a straight line, you're linear. And if you're not a straight line, you are nonlinear. Okay, a graph is really easy to see the difference between these two. Let's explore some examples of nonlinear functions when we look at the equations and when we look at the tables. All right, example number one in your notes. You're going to see that I have these little blocks of wood that kind of look like they're making steps. And we're going to take a look at what pattern we see in this table when we compare the number of steps with the number of blocks making those steps. Then what we'll do is we're going to graph and we're going to decide, is it linear or nonlinear? Okay, so let's take a look at this example. Well, it takes one block to make one step. And it takes 3 blocks to make 2 steps, 1, 2, 3, and it takes 6 blocks to make 3 steps. Well, let's take a look. Do we notice a pattern happening here at all? Every time we add another step, what happens to the number of blocks? Well, do you see how this is going up 2, and then this is going up 3? Well, if we continue that pattern, we can easily see that the number of blocks necessary here would be 10. It's kind of small. And then the number of blocks necessary here would be 15 to make 5 steps. Well, you might know already just by looking at this table. Does it look like the ones we've worked with before? Is it linear or is it not linear? Let's get this information graphed down here on a coordinate plane. So I want you to think of these as ordered pairs, 1, 1, 2, 3, 3, 6, and so on. Let's go ahead and graph them. 1, 1, over 1, up 1, 2, 3, over 2, up 3, 3, 6, over 3, up 6, 4, 10. Ooh, I'm almost off the graph. Now, if I connect these points, I'm going to get a nice curved line. It might be kind of hard to tell that this is curved, but I happen to have a pencil here. If I were to connect these 2 dots with my pencil, here and here, see how I connect those 2 dots at the bottom? If this was a continuous line, it would go straight up like this, but it doesn't. It curves. You can see it's growing 2, then it grows 3, then it grows 4 and 5. It's growing really quickly. So we see that nice curve. So is it linear or nonlinear? It's definitely nonlinear. Now, we noticed with linear patterns that this was a constant change. If this goes up 1 step, this should go up the same amount for each number. There should be the same pattern happening. So if here I'm going up 1 step and here I'm going up 2, then if I go up 1 step here, I should go up 2. Again, if this is linear, but it's not. This isn't a constant pattern. So we're seeing nonlinear. Now, I have challenged students before to write an equation that gets them from the x over to the y. What do I do to 2 to get 3? What do I do to 3 to get 6? What do I do to 4 to get 10? And so on. It's really a challenging equation. I'm going to tell you what it is. It's actually y equals 1/2 x squared plus 1/2 x. And if you're curious about it, you can try it. You can plug in the number 5 as your x here and here, and you're going to see how the output value of y is actually 15. Now, what are you noticing about this equation that we haven't seen before? Well, first of all, there's 2 x's. Second of all, there's an exponent, and linear functions don't have exponents. So that's one thing that makes this nonlinear is the equation itself, also the pattern in the table and the graph. Let's move on to example number 2. Here in example number 2, we're asked which function is a rule for the set of ordered pairs. So of these functions, which one of them is the rule for these ordered pairs? Okay. Well, you know what? It's always easiest to figure out the rule if we have all of our data in a table. So let's go ahead and just transfer those points into this table. 1, 1, remember this is X, this is Y. So 1, 1, 2, 7, there we have it. Okay, well, we're asked a question down here at the bottom as well. Is it linear or nonlinear? Look at how quickly this is going up. +6, +10, plus a whole bunch. Well, let's graph this really quickly. I've got 1 through 5 on the x-axis. So here's 0, 1, 2, 3, 4, and 5. I'm evenly spacing them out to use my whole graph. Now, my y goes all the way up to 49. I'm just going to count by tens. What if I count 10, 20, 30, 40, and 50? Again, just evenly spacing them out. Now, I'm just going to estimate here. If I graph the point 1, 1, over 1, up about 1, 2, 7, over 2, up 7, 317 over 3 up about 17, 431 over 4, 31's up here, and 549 over 5 and all the way up to about 49. You can see that this is not a straight line. It's actually curving. It's curving up. Now notice here it's growing really fast. It grows up 6 and then up 10 and then up a whole bunch. So it's growing not linear, but at a curve. It's growing pretty fast. So now let's look at our equations. This is, just by looking at the graph, nonlinear. And we know that a linear equation looks like y equals box x plus box, right? Some number times something plus or minus something else. Now, do you notice that this equation and this equation are both that of a linear equation? Both of them are linear. So we know that it can't be D and it can't be A because this is not linear. Do you notice how these two equations have exponents in them? I noticed that too. I bet that this nonlinear function has an exponent. Well, which of these rules is going to get you across the table? Let's test it out. Let's see. Let's just try rule C. It says to get y, take x squared and multiply it by 2 and then subtract 1. So let's just try this. Let's take this x and we're going to square it. If I take 5 and square it, I get 25. Then it says multiply it by 2. So if I multiply it by 2, I get 50. And lastly, subtract 1. If I subtract 1, does it take me across the table? Absolutely. It should work for every single point in the graph. That rule should work to get you across the table for everyone, and it does. Our answer here is C. So again, a nonlinear function had a rule that had an exponent in it, and we see a curved graph. Let's look at example number 3. For number 3, it says complete the table for the given values of x using this equation. They're giving us the input values that they want us to plug in for x. We need to come up with y. Well, we're also asked, is it linear or nonlinear? Take a look at it. What do you think? Do you see the exponent? Just by looking at this, seeing an exponent, we know that a nonlinear function has an exponent in it. Okay, so let's come up with our output values when we plug in each of these values for x. So I'm going to just start off by rewriting this, y equals 1/2, and in place of x, I'm going to put a parentheses squared. And then what I'm going to do is I'm going to figure out what's the output value for each one of my inputs. All right, I'm going to use a pencil for this. So if I plug in -3 for x, -3, well, -3 squared is 9. And if I take 9 times 1/2, that's 4.5. So my output would be 4.5. All right, let's plug in another input. We're going to plug in -2. -2 squared is 4, and 1/2 times 4 is 2. So my output would be 2. This is going to get messy. Let's plug in another one, -1. -1 squared is 1. 1/2 of 1 is 1/2. So I have 0.5 or 1/2. 0 is going to be pretty easy. If I plug in 0, 0 squared is 0. 0 times half is just 0. Now notice what's going to happen here. Let's see here. I'm going to plug in 1. Well, if I take 1 and square it, I get 1. And half times 1 or half of 1 is a half. See, notice that's what I got when I plugged in -1 too, isn't it? And then here, if I plug in 2, 2 right here for x, 2 squared is 4, and half times 4 is 2. Notice how, again, it's kind of like it's symmetrical here, right? So if I plug in 3, because I'm squaring it, it's just going to be the same answer as -3. 9, half of 9 is 4.5. So here's 4.5. All right. So notice that if I look at the pattern here, even though this is going up by 1 every single time, this is not consistent like it was when we saw linear, right? Let's graph it. -3, 4.5, -3, 4.5, -2, 2, -1, half, and then I got 0, 0. And then if I graph 1 over 1 up half, over 2 up 2, over 3 up 4.5, I end up with a parabola, which is actually a quadratic equation. We'll be learning about those later on in the year. Definitely, non-linear. Put some exclamation points there. It's not linear because it has an exponent. Ooh, I hope you're seeing that pattern here. It's got an exponent. All right, example number 4. We are cruising along. We're asked to complete the table for the given values of x using this equation. Take a look at the equation. What do you notice? Ooh, it has an exponent. Now, the exponent isn't a number. It happens to be a variable, but it still has an exponent in it. So right now, I'm probably sure it's going to be a nonlinear. It doesn't look like anything we've been writing for a linear function, right? Let's make a table. We have some input values for x that we're going to plug in. So we got y equals, let's switch the colors up. Let's use my favorite one, purple. Y equals 2, and we're going to raise it up to the power of x. So these are the numbers we're going to plug in for x. I'm going to plug in a 1 for x. Y equals 2 to the first power. That's 2. Let's plug in a 2 for x. Y equals 2 to the second power. That's 4. Let's plug in 3 for x. Y equals 2 to the third power, and that's 8. Ooh, there's a pattern. Let's plug in 4. Plug in 4 for x, just replacing the x with the 4. 2 to the fourth power is 16. Notice the pattern, double, double, double. And if I plug in a 5 here, that's going to be 32. Ooh, even though this is going up by 1, this is double, 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 double. That's growing really, really fast. It's actually growing exponentially, people. Let's graph it. We're going to see what happens. We're going to see if this is a straight line or not. Maybe you already guessed it. Okay, 1 through 5 on the x-axis. So I'm going to 1, 2, 3, 4, 5. Remember, if I'm going too fast for you, you can pause the video. Then I got to go up to 32. So maybe I want to count by, I don't know, maybe I count by fours. 4, 8, 12, 16, 20, 24, 28, 32. Holy buckets. Hopefully I didn't skip anything. All right, so let's graph this. Just real quick sketch. 1, 2. Remember, that's our first order pair. 1, 2. So over 1 up about 2. 2, 4. Over 2 up 4. 3, 8. Over 3 up 8. 4, 16. Over 4 up 16. And 5, 32. Over 5 all the way up to 32. Check it out. Connect it. Oh my goodness, not linear at all. It's very obvious. This is growing exponentially. Actually, this is an exponential function, which we're going to be learning about later as well. Get excited for that. So nonlinear. Well, why is it nonlinear? Because it has an exponent, people. I hope you're seeing that pattern. We're seeing it. Yes, we are. Okay, there's example 4. All right, last one, example 5. I bet you're having so much fun. You hate to have it end. Okay. So here we have y equals 2 divided by x. Hold on now. Is that anything we've ever seen when we've been studying linear functions? No way. Absolutely not. Now, we've seen things like y equals 2x, right? But if we think about this as a fraction over 1, the x is in the numerator. What's happening here? The x is in the denominator. Uh-oh. Let's see what happens. Is this going to be linear or not? I don't know. So we've got y equals 2 divided by x. Y equals 2 divided by the x. So we're going to plug in all of our input values right in here for x. Okay, so x is 1. Let's plug in a 1. What is y? Y equals 2 over 1, which is 2. Okay, let's plug in 2 for x. Let's make the x number a 2. So now y is going to equal 2 divided by 2, which is 1. Now we're going to plug in a 3. Y equals 2 and make the x a 3. Well, what's y now? Well, y is 2/3. Okay, now we're going to plug in 4. So we're going to plug in 4 for the x. So now y equals 2/4, which is actually 1/2. Okay, check this out. This is going up 1 every time. This is going, down 1, but then down a third, down. Yeah, this isn't very constant, is it? No way. Let's graph it and see what happens. Across the x-axis right here, we got 1, 2, 3, 4. So we're going to go 1, 2, 3, and 4. Be sure that these are all evenly spaced. Here's my 0. And then I've got to go, the y, the biggest number is 2. So I'm going to go way up here and make this 1, and I'm going to go way up here and make this 2. So I'm using my whole graph so you can see how this line or non-line is going to behave. My first order pair is 1, 2. So over 1 all the way up to 2, way up there. Then I got 2, 1. Over 2, up 1, plotting points. Then 3, 2/3. So over 3, up about 2/3 of the way from 0 to 1, so maybe about here. And then I got 4/2. Over 4, up about halfway. My graph isn't perfect, but you can see that I have a non-linear like curve here, right? So definitely not straight. Okay. Actually, we're going to learn later that if we take the x and we move it up to the numerator, it's going to be x to the negative first power. We're going to learn that later in chapter 7, which definitely makes this nonlinear because it has a negative exponent. So yeah, we can't have x in the denominator. No way. All right, let's kind of pull this all together and let's do a summary. I bet you could tell me this. A nonlinear function will have what in the equation? Did you say exponent? If you did, you're right. It's going to have an exponent, no matter what the exponent is. The exponent could be a number, like in these examples. Remember, this was the step problem. We also did this example. The exponent could be a number, or the exponent could be a variable. But if there's an exponent in any of the equations, it's going to be nonlinear. Okay? Now, what about this? What about this function right here? Do you see how there's an exponent? Is this linear or nonlinear? Don't be so quick to pick. Could I take this exponent and could I simplify it? 2 to the third power. Yes, I could. I could actually rewrite this as 5x plus 8. Now is it linear or nonlinear? It's linear. So be careful. Even though I see an exponent, if I can simplify it, and it makes a linear function, then it's linear. Can you simplify this? No. How about this? No way. Absolutely not. Okay, so hopefully you're going to see how these two things are different. All right. Now, I think that you guys are ready to do some practice. So you're going to be going on to your practice assignment on Schoology, and you're going to be looking at some examples of nonlinear functions and maybe some linear functions too. Good luck, everybody, and thank you for joining me.